this Cosmic Power Lines Part 2. In my wild imagination, sitting there with a glass of wine, I thought maybe I should call it Luke Skywalker, Don Skywalker Returns, or I Walk the Cosmic Line, but anyway. Sort of a continuation. You'll see this picture, I'm sure you have seen it, you'll see it over and over and over. It's one of the best, I think, the best redos of what a Birkeland current really looks like. Clearly it's out of scale, but that distance from the sun to the earth is 93 million miles, and you have to really appreciate the fact, let's see if I can do this without shutting the system down. You really have to appreciate the fact that this distance is a tremendously amount bigger than this distance across here. And for years, before Birkeland even proposed this sort of idea, it was just absolutely considered dingy for anyone to think that charge could make that 93 million mile journey without either dissipating or not being able to get through because it was a vacuum, and clearly you can't go through a vacuum, charges can't go through a vacuum. So finally, of course, as I said the other day, after we threw some rockets up there into the ionosphere, we showed that indeed, yes, this is what happened. And so I think it was 2006, something like that, NASA announced that they had found a 30 kilovolt space battery. And that's indeed what powered what is it, a magnetic flux rope that drew all that energy from the sun and stuck it down into the aurora. That's not true. I mean, I give them credit, at least in the red there, I hope you folks can read it. It says flux rope pumps 650,000 amp current into the Arctic. Well, they got that right, at least. I don't know what the 650,000, but it's a lot of amps. But the 30 kilovolt battery, I'm not sure. So certainly nobody's ever found any voltage source out there. Most of the time, we presume that these Birkeland currents have their current in them because that current has been induced by the conductor plasma crossing a magnetic field. And when you push a conductor through a magnetic field, you induce a current. That's the way the current is generated. It doesn't come from a battery of any sort. There is this picture, and at the risk of being too repetitive, I would like to emphasize the fact that they got that right. That is exactly the way, at least the inner beginnings of a Birkeland current look. When you're right at the center of that, you can see the little arrows are going from right to left. Those arrows indicate the direction of the current density and the magnetic density. And then as you work your way out, radially out from the center of the core, both the current density and the magnetic field begin to wrap around. It begins to have what's called an azimuthal, fancy word, let's not use the word azimuthal, but it begins to have a wraparound component. So as we get farther and farther out from the center of this, you can see that wraparound field and current density gets stronger, and the axial, that is in the direction of the axis of the current, gets weaker. Until finally you get out to the outer surface that they've drawn there, and the magnetic field, together in parallel with the current density, is completely wraparound. That's about 1/4 of the story. And it seems strange that they stopped there. Stig Lundquist, who did this model before me, for about 50 years before I got there, he'd stopped there. Even good old Hannes Alfvén, where you ask him to draw a picture of a Birkeland current, he'd draw something that looks like that. That's a very incomplete picture because you can just think of continuing on. Go out to the next little distance out from the center of this. What do you think happens? Nothing? No, the axial current, which has gone to zero at these outer, what should I say? Maybe can I do this again? Yeah, out here, where the axial field has gone to zero. In other words, all you have is wraparound here. For the next step out, the axial field actually reverses and goes back this way. And so what you get is you get a wrapping that goes around this way. And so a Birkeland current consists of wrapping one way and then back wrapping down the other way, up one way. And as you get farther and farther out, these wrappings keep getting bigger and bigger. And I think, I didn't say it the other day, but there's an analogy to the Roman fasc, you know, fascism. You take a little bunch of sticks that are very pliable and breakable, and you wrap them with a leather strap, and wrap them this way and then wrap them that way. If you do it well enough, you can get something that's as strong as a steel beam. So that's the reason. It's this continual redirection of the wrapping of the magnetic field, a la the fasc, that gives this thing its structure, and it gives it its strength, and it's the reason that Birkeland currents can carry current 93 million miles without doing like a garden hose would do, you know, dissipating. It stays collimated. And in fact, the longest one that I know of is the jet out of M86, I think it is, Galaxy. And M86 has a big long jet. Birkeland current is what it is. And it goes for something like, I don't know, at least some number of light years, straight as an arrow. It does not dissipate. And that's the reason. Well, anyway, just to go on, the idea of stars on a string, I don't know how many of you have ever looked at astrophotographs. Like, I'm a nut for taking astrophotographs, and every time I look at one of my images that has a lot of stars in it, I start plotting out, oh, look at this, there's these guys, they're all on a string, and here's another string that goes this way. And if I ever said that to a professional astronomer, he wants to lock me away anyway, but I'm sure he'd say, this guy's nuts. The stars don't form on strings, you've got to be kidding. Well, actually they do. And the thing of it is that sometimes those strings are visible because the plasma is in glow mode. You can actually see it, like the aurora, for example, or the sun's corona, that's glow mode plasma. Sometimes it's dark mode, and you don't see the strings. And the astronomers say, ha, see, they're not there. They're there, you just don't see them. So anyway, my point is they really no longer laugh. But the connections are not strings or molecular gas columns. They're plasma. They're the plasma that make up Birkeland currents. And I just said that sometimes they're visible, sometimes they're not. And stars and galaxies form at pinches, the so-called Z pinch, that occur along Birkeland currents. And you saw Tom in the last lecture had a picture of this, and we all love it. And so you can't hear a lecture here without seeing a picture of M29. But I think it's so appropriate, so appropriate, that you can see there the double layers here. See, there's an outer layer and an inner layer here and here. See it out there, see it here. You can see the pinch. You can see that the strongest current is in here because these things, these white globs, are double layers. This is a perfect, in my mind, and I think in many of our minds, perfect representation of Dave Tabbitt loves the word archetype. This is an archetype, or if you're an engineer, prototype. This is the basic model. These Z pinches are all variants of that. And we'll come back and talk about some of those properties. And I would say I'll speak for Wall, I'm pretty sure he agrees with me, and I and some others, believe that that's the way stars get formed. What you're looking at there is not the death of a star, which is what a professional astronomer at least used to call it, They're getting off of that now. I've actually heard one say that's the birth of a star. You got it. That's the birth of a star. Because when that thing pinches together, that bright object in the middle is condensing. It's not dying, it's not dissipating. So we think that that's how our sun was created. And I unabashedly stole that from Wall. You can see his name on there, I think. It should be on there someplace. But Wall made that up. And so what you're seeing there, on the left at least, is this is the Birkeland current, and there's a pinch across here. Now, if I were to do this over, and I'm not about to even try, this region here and this region here might be slightly closer together, so that this would curve out, and this would curve out, this would curve out, and this would curve out. And so you get something that looks more like that M29, like I use the phrase, two torpedoes who bucked heads and actually penetrated a slight distance into each other. So it's kind of like two dolphins or something who came together. Those white things that I was showing you when the thing went berserk are these things here, these double layers. And they are well known to form any place where the current density and the voltage gradient are high. And what is this? Well, this is the center core of the Birkeland current. That's where the current is highest. So I guess what I'm trying to say is everything sort of jibes. And these regions here are where the so-called E and A, the energetic neutral atoms, that were discovered by Ibex form. And this is, of course, a two-dimensional shot in a cross-section through a three-dimensional object. And so what you're talking about here is a ring. And Wall has sort of, he showed it over here. There's that ring. And if you remember from the other day, I showed you Tony Peratt's witness plate taken of a slice across through a Birkeland current. And he had put those little circles all the way around and said, those are where the filaments are. There are 52 of them or something like that. And there's the little bright dots. That's an actual photograph of a nova. And so we think that, a nova, something new. Boom, you squeeze it, pops a new star. So in sort of in the halfway view, there's this thing here. In order to sort of clarify what that diagram on the left looks like, I came across this, and I wish I could give these folks credit. I don't know where I got that, so I'm maybe in trouble with the patent department or something. But this is pretty much what we think happens. You can see the pinch. You can see that this is how I would redraw Wall's diagram. It's just a little bit of a pinch there. If it was up to me, I would take this purple line and come down and connect it around the bottom of this and come back out that way. Bring this purple line up, come around the top and bring it down this way. And that would isolate this, it's not a sphere, a sort of I don't know, what is it, an oblate spheroid? That's sort of a ball, an egg shape. And that's our heliopause. Our heliosphere, the outer edge of it is the heliopause. Also notice, don't mistake you notice the green curlicues. That's the twisting magnetic field that's going down through there. And there was also, I think one lecture or two ago, I drew that. This diagram here really, I kludged this up. This is a Photoshop cheat, I must admit. What's not a cheat is the sphere and this tail were reported by the Ibex mission. And I was so convinced that there had to be two tails on this thing, one going one way and one the other, obviously representing this part of the Birkeland current and that part of it. You can't have half of it. What do? You're going to cut it in half and that's it, not have the other half of the Birkeland current. It has to be there. So I drew it in there anyway. I'm sure if an astronomer had caught me at it, he would have loudly booed. But in any event, if you go back and look at that and compare those two diagrams, I think you'll see what Wall and I are getting to. That's the way stars are formed. And if you pinch a Birkeland current, just think of it yourself, you don't have to be an engineer. If you squeeze a pipe, what you're doing at the point of the squeeze is increasing the current density. You're not increasing the current in it. There's the same number of gallons per minute coming down here as there is in the middle of the pinch, and the same number. The amperage in a wire is always the same, whether the wire gets fat or skinny. So here in the middle of this thing, you're creating a pinch, and so therefore the current density gets higher, and if it gets higher, then the plasma gets brighter. Plasma gets brighter when you increase the current density that it's carrying. In any event, there's a sort of a schematic diagram that I made up. This is totally me. It shows, I think, what I was implying that I would like to see, and that is a pinch effect here. The bluish is the ibex ring. That's that blue circle, and it is indeed a circle, hopefully. In green, it's not too easy to read, but on the left it says the interstellar magnetic field. Well, that's coming down along here and coming down along here. It's also coming down in the middle. And if you see right about in here and right about in there, there's a twisting magnetic field, and it's getting tighter at the bottom. So it starts off big, and then it funnels down and eventually becomes quite intense at the point of the Z-pinch. Those twisting magnetic fields are important, and so remember them, you'll see them again. If I impose the picture of M29 on top of this, forgive me for doing it, but that's the general idea I'd like to get across. The green sort of blob here and sort of here down here is very reminiscent and fits very well with those mysterious gamma ray bubbles. I don't know if any of you have heard of them, but they have been discovered in just those positions above and below our galaxy. So you say, well, maybe I thought you were talking about a star. I am. But I'm also talking about a galaxy because it's our feeling that this method, this formation mechanism, if you will, is scalable. It explains how stars are made and also explains how galaxies are made. The only thing different is one of scale. You got to have a real big Birkeland current to form a galaxy, obviously, and a much smaller one to form a star. Yeah, and also we feel that the sun and the planets and other members of our solar system live within the volume defined by the pinch. That's the, I guess you can see it, that's the, this volume right, it's that egg-shaped, or is it oblate or prolate spheroid? Oh, I think it's oblate, it's fat. Anyway. Just recently, this headline came through. Sun may blast 2 jets of plasma into interstellar space. Ooh, I was right. 2 tails. I should be not so braggadocio, I'm sure, I'm sorry. But anyway, this is the latest idea of what astronomers think the heliosphere looks like. It's there. To me, I don't know, I watch CSI too much, I guess. I mean, it looks like something that comes out of a forensic pathologist's laboratory. But obviously it has 2 ends to it. It isn't exactly in the shape of an oblate or spheroid of any kind. It's a blob. But the one thing I will call your attention to, it says here on the bottom, notice the spirals, which is the magnetic field surrounding the heliopause. I'm not referring to the red, I'm referring to the things, the spirals that wrap the heliopause, okay? And so that is important. At least we've got the powers that be to realize that yes, this heliopause is two-sided, it's got magnetic field into it, and it's wrapped with at least a helical magnetic field. Here's another, this is of course just an artist's impression, but I think that is probably more like at least the theoretical, the archetype model. And the important thing there is that you'll notice that the white lines are I hate to use the word field lines because it's a touchy subject with me, but it shows the fact that the magnetic field wraps both ways, okay? This next one is very much like one that Tom had on. And with one minor exception, it's all wrong, in my opinion. We have the accretion disk, we've got the black hole, we've got the event horizon, and it's all nonsense. This is the astronomer's explanation for what you just saw at M29 or the other drawings that I just showed you. The one thing they have right is the magnetic field lines. You see the spirals coming down? So a cross-section of the Birkeland current at the location of the pinch contains the spiral paths of the magnetic field. That's true. That's correct. There is a spiraling, sort of looks spiraling anyway. We'll talk about that in a minute. So if we look down at the cross-section, the cross-sectional disk, which is really, the disk that's defined by that ring of the energetic neutral atoms, the ibex ring that we just got through looking at. We should see a spiraling magnetic field. The little blowout diagram with the event horizon, the black hole, and the accretion disk is a total F. It fails. Don't believe it. Anyway, here's some diagrams that the team that ran the Ulysses space probe, the one that went up as high over the poles of the sun as anything has ever gone, to take a look at what's going on at the sun's poles. We never really have gotten above the poles. But as close as we've gotten, you can see here that what is coming out of the bottom of the sun is this ever-widening spiral of a magnetic field. And if you look at the North Pole, which Ulysses also did, you see the same thing. I think the diagram here is a little bit more accurate and a nicer diagram. But it essentially has the same material in it. Notice that the green disk on the solar equator, here they don't show any spirals, any spiraling in, but they do show that ring, which is the E and A ring, and they do show the magnetic field lines that are circling around. And this, I submit to you, is very characteristic of a Birkeland current. In fact, it looks exactly like that, and you all probably recognize that. I mean, many of you, I'm sure, do. That's Eugene Parker's description of the solar magnetic field. You remember the words, the magnetic field of the sun swirls like a ballerina's skirt and has ripples and disappears into infinity. Well, it doesn't disappear into infinity. That's one of the things that got me into this, was when I heard astronomers talking about magnetic fields that went to infinity. Magnetic fields are closed paths, so they can't go to infinity. So sorry, Gene, that's not right. But the idea of a spiraling like this as we get close to the equatorial plane of the sun is quite correct. What he's also shown in there, if you look very closely, I don't know if you folks can see it, but you notice inside here that you can see the orbits of the inner planets, and this is probably Jupiter or Saturn around out here. So I claim this spiral is what would be expected from an interstellar-sized Birkeland current. At the plane of the disk, the cross-section might look like, okay, here we go, that. Now, I think you've seen that diagram before. That's from my model of the Birkeland current, and I should say Stig Lundquist and my model of the Birkeland current. If we can do this again, yeah. Let's talk a little bit about what the meanings of all these little black arrows are. First of all, the radial distance out here is totally arbitrary. That's just a distance scale I put on it. It means nothing at all. It's just 1 through 220 or something like that. But it's to give a feeling of how far out from the center of this Birkeland current we are. This is a typical Birkeland current. It's a cross-section. And I'd like to explain, or try to get you, we've done this once, maybe you've heard me do this before, but I love the explanation because I think it makes a lot of sense. The salmon-colored rings, those rings and the darker one right in the center indicate where matter goes, where matter condenses, where matter is shoved. And what shoves it? Well, when the Birkeland current is out in space and is floating along happily, like halfway between the sun and the Earth, that condensation of matter does not occur. The model does not support it, and we don't have any observation of it, so it probably doesn't happen. When that concentration of matter happens is when you start to squeeze the Birkeland current. And you can squeeze it either by putting it into a Z-pinch, or you can squeeze it by putting it down, you know, the lotus-shaped funnels that are above the North Pole and above the South Pole, because your magnetic field is squeezing that Birkeland current. When you squeeze the Birkeland current, what happens? The current density goes up. You're not going to change the total current, but you can change the total current by pulling the belt tighter. So that means what? Well, let me just sort of give you sort of a thought experiment, if you go along with me. The black arrows that we have shown here, this one here that goes, this first inner one goes around clockwise, right? The next one out goes around counterclockwise. If you look very carefully, you can see each one of these circular black lines has an arrowhead on it. This is clockwise, this is counterclockwise, this is clockwise. So we talked about the counter-rotating cylinders. Those black arrows indicate the presence of rotating surfaces, cylinders, if you will, of both current density and magnetic field. Magnetic field and current density are parallel. They're lined up. They're not fighting each other. That's the way where they want to be. But if we then squeeze this thing, what we're introducing externally to this is we're introducing perhaps an increase of current, maybe right there. Actually, we're increasing the current at all points, at all radial points. Current going away from us, a current density, okay? We're squeezing it, the current density that this thing is carrying is going away from us, and so it's getting bigger, it's getting stronger. So think about what happens. Let's say at a point right there. I'll take the dot away and see that arrow, okay? You can see that if your current density is increasing, going away from you right at that point, then what is it crossing? This circle, the circle that it's crossing, this circle here, is in the clockwise direction, right? So it means that at the point that we're discussing, right there, the magnetic field is straight down. So you've got this current going into the diagram, and the magnetic field is straight down. Okay, there's a thing called Lorenz's law. If you don't want to understand it, shut your ears off for 30 seconds and then come back in. Lorenz's force law says if you've got current going one way and you've got a magnetic field going another way, if you want to know what's going to happen to the forces on those particles, those positive charges that are moving, Put your fingers in the direction of the current. Okay, that's into the diagram. Then rotate your hand, your fingers, to the direction of the magnetic field, which in this case is down. Okay? So current in, magnetic field down. Your thumb is going to give you the direction of force on that stream of particles. Okay? So what I'm claiming is that at this point, if I have it, I think I have it. No. Maybe I should do this. Forget that. Yeah, let me go back to it again. Yeah, can't get rid of it. Anyway, at that point, what you're going to have is a force. See that black arrow there? Horizontally pointing toward the left. That's the additional force on those particles, in addition to the downward force of that clockwise stream. So you got some particles that want to go to the left, some particles want to go down. What happens? Well, they both happen. So you get a sort of a 45-degree angle. And before I screwed up my diagram, maybe you can see it over here. See, that's the similar kind of a situation that happens here. You got a downward flow, you got an inward flow, and the combination of downward and inward is this guy down here heading to the southwest a little bit, okay? I won't go over every one of these, but if you look at each one of these little tiny black arrows, I've drawn them in such a way that you begin to see, like for example, look at this collection here. It looks for all the world like there's a spiral. If you're moving like this, you're spiraling in. If you're moving like that, you're spiraling out. Which way are you actually spiraling? Answer, you're not. Because if you look at the direction of the little arrows, half the time the arrows are pointed one way and the other half the time they're pointed the other way. But taken all together, they look like a spiral. So I'm going to claim that you will see in the cross-section of a Birkeland current, you've already seen it in Tony Peratt's witness plate, you will see what looks like spirals. They are spirals, but they're not indicative of any flow, because half the time the thing is going in and half the time it's going out. Go a little further, it'll go in, come in, and come out. So that's where the spirals come from, I claim, at least. Okay, long discussion, and I apologize if I turn anybody off by that. But all this comes down to, okay, am I still all right? Sorry, my beard itches from the microphone. There are preferred radii at which matter may tend to accumulate. And I think what I've tried to show you there is that on certain of those circles, matter will be pushed out, and other of those circles, matter will be pushed in. And can we go back to that slide? Let me just say one thing. If not, don't worry about it. Okay, forget about it. Oh, okay, swell, good, thank you. Here, that one, okay. You can see there that, perhaps you can see, if I asked you to describe to me in words, where does the matter accumulate? You probably have a hard time. Let me give you my suggestion of how to describe it. One of them, look at this salmon-colored disc, this guy here. Matter will tend to accumulate in there at a place, at a higher radius than this counterclockwise rotating field. Okay? When the wraparound field is negative, counterclockwise, out beyond that, you get matter accumulation. At this point, that is on one of the clockwise, that is to say positive wraparound fields, matter will tend to accumulate inside that at a lower radius. Okay, so you can write it down. Matter will accumulate above, that is at a higher radius than the counterclockwise current and at a lower radius than the clockwise. Okay, remember that, write it down on a piece of paper. We'll come back to that in a second. My thesis is this: if our sun was sitting there in space, fat, dumb, and happy for millions of years, but it didn't have Earth, Mars, Venus, and Saturn, had all the other planets, or most of them anyway, and along comes this Herbig-Haro object, or this shish kebab of planets, as we think happened. And that shish kebab broke up. It would be kind of like, if you can visualize, you're in a gambling casino and you've got a roulette wheel, and some guy comes along with about 3 or 4 marbles and throws the marbles in the roulette wheel. Where do these things settle out? My contention is, if you do that, and if that's what happened, those planets would probably settle out in those regions where matter accumulates. It's certainly not going to go to a region where matter is sucked out of. Okay? Is it sure? No. But let's, for the sake of argument, let's say that's maybe what happened. There is this Titius-Bode series, and I'm sure you probably, has anybody has not heard of this? It's a mathematical structure, mathematical formula that tries to predict in astronomical units the positions of all the planets, the radial distances of all the planets. By definition, 1 astronomical unit is the distance from Earth to the sun, 93 million miles, okay? And so if you look at this Titius-Bode thing, I don't need the pointer, you can see it there yourself. The radius is 0.4 plus 0.3 times 2 to the m. Well, okay, try it out yourself. If Mercury is, well, just do the easy one. If Earth is m equals 1, okay, you stick a 1 in there for m, so you get 2 to the first power, that's 2. Running this formula backwards, you get 2 times 3/10 is 6/10, plus 4/10 is 1. You got the right answer. And the same thing goes for Venus. If you try m equals 0, 2 to the 0 power is 1. So 3/10 plus 4/10 is 7/10. And that's right for Venus. Venus is 7/10 as far away from the sun as we are. And Mercury is 4/10. So when you have m equals minus infinity, the second term after the plus sign in that equation goes to 0, and you end up with 4/10. So it's right. And it actually, you can do it for Mars and Jupiter and Saturn and so on. And it sort of gives you the right answer. Let me make a claim. You can either accept it or reject it. I claim that the doing of this is numerology. It's data fitting. You can fit a curve. If you take 9 planets, 9 points, and give me the ability to write a 10th order equation, I can make it pass exactly through each one of those 9 points. So it's no big trick. This one is kind of nice in that it's a simple little equation, and it seems to work, sort of. But it is not based on physics. It's based on, yippee, I found the right answer. It's a numerology thing. It's clever tricks with numbers. It's not based on the physical ideas about what's pushing on what. There is a paper that was published, and I'm not sure, I'd love to have on my screen the number of minutes that I have left. Can you do that? I don't know if that's possible. If I try to do something like that, it may crash the 747 again, I don't know. Well, at any rate, there was a paper published in 1990 by a fellow by the name of Wells, and he came out with this diagram and these results. And he's quite right in what he did. His interpretation of it, I think, is wrong, but let's just think about it. What he's got plotted here in the curves here, the J1 is Bessel function J0 is the 0th ordered Bessel function. That's a plot of the axial magnetic field and the axial current density. And so you can see, and the horizontal, the abscissa, this thing, the x-axis, if you will, is the distance out from the center of the Birkeland current. This has nothing to do with time. Every time people see a wibbly-dibbly diagram like this, they say, oh, this is a function of time. No. This is a function of distance out from the center of the Birkeland current. And what this says to you is that at the very close to the center, right at the axis, the axial field is a maximum. It never gets any stronger than that, ever, no matter how far out you go. And the other curve, the J1, this curve that starts at 0 and goes up, and you can follow it, it's the second curve, that's a plot of the wraparound field. So you can see that at a point such as 0, the wraparound field is 0. The axial field is a maximum, 1, normalized to 1. And so the thing is, like that little diagram showed, it's straight down the arrow, down the road. But then the axial field gets weaker, and finally here goes to 0. Meanwhile, the wraparound field is getting stronger, and it's still almost exactly, not quite, but almost at its maximum when the axial field goes to 0. That's when it's totally wrapped around. So those diagrams that you see, you know, the barber pole picture of the familiar Birkeland current picture that you see all the time, it takes this plot from 0 to right about there. That's all I do. And when I say, yeah, but then it starts to go back the other way, you can see what I'm saying. This is the axial field strength, and it does indeed go negative. Reaches a maximum in the negative direction, and then comes back up and goes to 0 again. So if you think about those black circles with the arrows on them, showing you how the field and the density are rotating counterclockwise and clockwise, you can see that the J1 here is positive. The field is going around in the clockwise direction. Here it's going around in the counterclockwise direction. And what did we say? Where does matter accumulate? It accumulates, well, if you go back, you can see that it ends up accumulating at a point exactly like that one. That is really the first, other than that central glob that's always heavy, the first concentric circle that is a place where matter condenses is right there. And just to make a long story short, if you want to describe it in words, nothing to do with physics, this is a maximum of the axial field. Here's the axial field, and right at the center of the thing. The next time that axial field is a positive is right there. The next time it's a positive maximum is right there. Wells, the fellow who published this article, said, no, the places where the planets are going to be found is at the extrema. That is to say, it can be a negative maximum or a positive maximum, negative maximum or a positive maximum. He left one out here, but that's all right. I don't see any physical reason for that, because the negative maximum of that axial field is the region where matter is sucked away from. In order to get it to accumulate at certain places, you have to suck it away from other places next door. Okay, anyway, enough of that. That's what he did, and so here's what I did. You can see it's a very similar plot. The black curve there is the axial field strength. The red curve is the wraparound field strength, and you can see when one is a maximum, the other one's 0, and so on. Another thing I have to quarrel with Wells is the title. I don't know if you caught the title of his paper. It had to do with the planets will be located at energy minima. Energy minima. Well, the energy in the magnetic field is proportional to the magnetic field squared. So that, I still would like to know how much time I have. How long is it? I'm out of time now? Okay, let me just quit. What you can see is that there's the plot, the intensity plot. I will go as rapidly as I can to where things, there's a plot. You can plot those Bessel functions. That's an Excel plot. The latest version of Excel, you put in a number, it'll give you the Bessel function. There is a sort of a, I would suggest you look at the average astronomical unit distance of the planets and look at the value that this method of mine, putting the planets in those places where data accumulates at 0.39, at 0.36, 0.72, 0.69. It's a pretty darn good match. If you want to compare it to Titus Bode, or Titius Bode, I should say, or Wells, I've done that as well. And I think I'm still pretty good. I'm still in the ballpark. I'm not as good as Wells in certain ones. But of course, like for Earth, they just said, by definition, it's 1. I let mine go, I did a least squares fit as to what the scale factor should be. And the scale factor comes out about 19. Anyway, notice, just the last thing I'll say, and then I'll leave you. Notice that Pluto, in the bottom row, actually the average is around 39 or 40. Titius Bode says it's at 77. So you can see that numerology business of fitting the curve to the numbers may fit almost perfectly for Mercury, Venus, Earth, Mars. But when you get out far enough, it doesn't fit. Whereas Wells and mine, I think, both of us are pretty much on the money. I think the difference, why do I claim mine is better? Because mine is based on the physics. Wells is based on wrong physics. He said, he saw where those zeros were, the Bessel function. He said, oh, put them there. But he's got some of his planets at places where the planets would be swept away from, not attracted to. Anyway, if I can just go, why don't let's go. Let's go, let's go, let's go. I want to get you folks out of here, and I hate people who run over like I'm doing. Here's my last example, the galaxy M64. It's known that there's a counter-rotating cloud bands have been observed here, and what happens is that half the stars go one way and half the stars go the other way. So it's an absolute counter-rotating cloud. Are they caused by rotating Birkeland current sheaths? If so, this would be a beautiful confirmation of what I'm saying. Anyway, I claim that Birkeland was right, in perhaps more ways than he knew, and for the following reasons. That is a picture of the Birkeland web, if you could see it all. That includes, this is an artist's rendition, but it looks pretty much like what we think is out there. And as Wall has said many times, everything is interconnected. Us to the Earth, the Birkeland current from the Earth to the Sun, and the Sun up to the galaxy, as per that diagram I showed you. And those connections are electrical. Oh, I'll just end with another look at that picture, and my comment is, Birkeland just found the first link in the network, but it's all connected, everything. Us, the universe, everything. Thank you.